Welcome back, everybody. This is our third class in NEET previous year questions for chapter Dual Nature of Matter and Radiation. Before this video, we have made two videos in this series, and both of those videos are available on our channel's playlist section. And there are other videos are also available. And if some of your friends are preparing for JEE or you want some additional practice from JEE previous years, then those are also available in the channel's playlist section. So you can go and watch those videos, and if you find these helpful, useful, then do press the like button, share them, and subscribe to our channel. With this, let's start today's video. In the previous one, I think we covered up to question number 30 or something. Yeah, I think that was the last one. Now we will start with 37. So here the energy of photon of light is 3 electron volt. The wavelength of the photon we have to find out. So for that we have the straightforward relation that E is equal to hc by lambda, and that is 1240 electron volt nanometer. That is the value of hc, and divided by lambda. Now E is 3 electron volt, so what we can write? We can write lambda will be 1240 electron volt nanometer divided by 3 electron volt. Electron volts get cancelled, and this will give us 413 nanometer approximately, and that matches with option B here. Moving to the next one. If the threshold wavelength of a certain metal is 2000 angstrom, the work function of the metal. So again, as for the previous one question, here E will be hc by lambda, and that will be equal to 1240 electron volt nanometer divided by 2000 angstrom. That can be written as 200 nanometer. So from this, nanometer gets cancelled, this 0 gets cancelled, and this will go on. We can cancel it on 2. So this will give us 6.2 electron volt, and that is basically option B here. So with this, let's move to the next one. 39, question number. If c is the velocity of light in free space, the correct statement about photon among the following are. So we have been given some statements regarding photon. Now we know that energy and momentum relation for a photon is something like this, that E square, here E is the total energy, is equal to m square c4 plus p square c square. Now for a photon, its mass is 0. So this relation gets converted into that E square is equal to p square c square. P is the momentum of photon, c is the velocity of the photon, and we are assuming that photon is traveling in the, or light is traveling in vacuum, so that's why we can take its speed as c. So from this we can write E is equal to pc, and from that P is equal to E by c. Now we know that energy of photon can be written as h nu, h times nu, and here c is as it is. So momentum can be written as h nu by c, and that is statement 3 here. So statement 3 has to be a correct statement. So out of the all given option, uh, statement 3 should be there in the correct option. So we can see here in option 1 it is there, in option B it is there, in option C statement 3 is not there because we have to find the correct statement. So option C is cancelled, we can say, and option D is cancelled. Now between option A and B, the difference is of statement 2. So let's see the statement 2 here. The velocity of the photon is c, and we have already discussed it that we assume that photon is traveling in free space, so its velocity will be equal to velocity of light, that is c. So second statement is going to be right here. So if second statement is right and it is not included in option B, so we can neglect option B also. So option A will be the right answer here. With this, let's move to the next one. The number of photons per second on an average emitted by a source of monochromatic light of wavelength 600 nanometer when it delivers power of 3.3 into 10 to the power minus 3 watt will be. So we have to find out number of photons, and we know that number of photons can be found out by power divided by the energy of the photon. Now here power is mentioned to us, so we have to just find out energy, and energy will be equal to h nu, and that can be written as hc by lambda. And here energy has to be in joules, so we cannot directly put hc is equal to 1240 electron volt nanometer, so because we have to convert it again, so we will substitute their original value. So h is given as 6.6 10 to the power minus 34, c is 3 into 10 to the power 8 divided by lambda, that is 600 nanometer, so 600 into 10 to the power minus 9. So this can be written as this will go on 200, and this will on 100, and this will on 3.3. So this can be written as 3.3 into 10 raised to power minus 34 plus 8, and these two will give them negative 7, that will go on as plus 7. So 3.3 into 10 raised to power minus 34 plus 15. So basically this will be minus 90. Now let's go to the calculation of n. So n will be equal to p, that is 3.3 into 10 raised to power minus 3 divided by 3.3 into 10 raised to power minus 90. So this get cancelled, and we will get 10 raised to power 16 photons per second. So that is option C here. With this, let's move to the next one. Light with energy flux of 25 into 10 raised to power 4 watt per meter square falls on a perfectly reflecting surface at normal incidence if the area is 50 centimeter square. Average force exerted on the surface is. So here, as mentioned, here we have reflecting surface. Now for reflecting surface, we know that change in momentum due to reflection will be twice the intensity divided by c, that is change in momentum. Now, and force will be 2I by c into area. Oh sorry, I misspelled a term, that this is not change in momentum, this is basically pressure, the pressure exerted, that is 2I by c, and from this we can calculate force, that is 2I by c into a. So let's substitute the values. Twice I, that is 25 10 raised to power 4 divided by 3 10 raised to power 8, area 15 into 10 raised to power minus 4. So when we calculate, I think this will go on 5. So this will give us 50 into 5, that will be 250, and these two gets cancelled, and here we get 10 raised to power minus 8. So that can be done as 2.5 into 10 raised to power minus 6. That is option B for us. Let's move to the next one. A 200-watt sodium street lamp emits yellow light of wavelength 0.6 micrometer, assuming to be 25% efficient converting electrical energy to light. The number of photons of yellow light emitted per second. So here we have 25% efficiency, and we know that number of photons emitted are power by energy. Now energy of a photon can be written as h times nu, and here it will be p, and nu can be written as c by lambda. So this is the basic relation here we have. Now as mentioned that our power efficiency is 25%, so our actual number of photons will be 25% of this, or we can say 25 by 100 times of p lambda by hc. So 25 by 100 will be, we can say keep it as it is. Let's substitute other values. P is here 200, lambda 0.6 micrometer, so 0.6 10 raised to power minus 6 divided by h, that is 6.6 10 raised to power minus 34, and here from this C, that is 3 into 10 raised to power 8. So what we can do here, this will get cancelled on 2 and we can cancel it on zero point 0.1, means divided by 6, and this will give us 1.1. And so this can be written as like this: 25 into 2, that will be 50, into 0.1, that will be 5, divided by 1.1 into 3, that is 3.3, into 10 raised to power, this will give us minus 6, this will give us plus 34 and minus 8. So 5 into 3.3 into 10 raised to power 20 basically. And we know this will approximately will be equal to 1.5 into 10 raised to power 20, and that is option A for us. Let us move ahead to the next one. A source S1 is producing 10 raised to power 15 photons of wavelength at 5000 angstrom. Another source of photons per second of wavelength 5100 angstrom. Then the ratio of power S1 and S2. So here we have been given number of photons, and we know that number of photons is equal to power by energy, and that is Phc by lambda. So here H is constant, C is constant, so we can say number of photons are basically proportional to power times lambda. So from this we can write N1 by N2 will be equal to P1 lambda 1 divided by P2 lambda 2. So N1 is 10 raised to power 15, N2 is 1.02 into 10 raised to power 15 is equal to P1 into lambda 1, that is 5000 angstrom, divided by P2, that into 5100 angstrom. So these two gets cancelled and zeros gets cancelled, 10 raised to power 15 gets cancelled. So basically relation is 1 by 1.2 P1 by P2 into 50 by 51, and that can be written as 100 by 102. Let's multiply 2 on the both side, and these two are same. So we can say here P1 is equal to P2. So powers are same, our ratio is 1. That is option A for us. Now moving to the next one. The momentum of a photon of energy 1 MeV in kilogram meter per second will be. So we have to find momentum of a electron, and we know momentum of photon, and we know that for a photon what we have, E is equal to Pc, and from this P is equal to energy of the photon by C. Now energy of photon is 1 mega electron volt, so that will be 1 into 10 raised to power 6, and that is in electron volt, so 1.6 10 raised to power minus 90 divided by C, that is 3 into 10 raised to power 8. So this will give us 0.5, and this is approximate, into 10 raised to power minus 30 on the upper side, and this 8 will go as negative on the. So zero point 0.5 into 10 raised to power minus 31 or 21, and that's can be written as 5 into 10 raised to power minus 22. That is option A for us. In the next one, the value of Planck's constant, and that is well known to us, that is 6.63 into 10 raised to power minus 34 joule second. And if you confuse about the units, then how you can find out? You can find out that E is equal to h nu. So unit of h will be energy divided by frequency. Now energy has a joule, unit as joule, and frequency as second inverse. So this will be joule second. That is option D for us. In the next one, momentum of photon of wavelength lambda. So we know that energy of a photon is equal to P times C, and it is also H times nu. So if we compare these two, then momentum becomes H nu by C, and it is not given here. So what we have to do, we have to convert C in terms of we can say convert C in terms of frequency and lambda. or we can say basically convert frequency into lambda. We know that C will be equal to frequency times lambda. So from this, frequency is C by lambda. So this will give us H by C into C by lambda. C gets cancelled and this is H by lambda. That is option A for us. Next one, the wavelength of a 1 kilo electron volt photon is given by this value, frequency of 1 MeV photon. So we have to find out frequency of 1 MeV photon. Now, you might have a doubt that we can directly calculate the value of, we can say, frequency of 1 MeV photon. How? We know that energy is equal to H times nu. So from this we can find out frequency is E by H. So here we have energy, that is 1 mega electron volt. So 1 into 10 raised to power 6, and that is in electron volt. So 1.6 10 raised to power minus 19 divided by H, that is 6.626 10 raised to power minus 34. So we can calculate via this method, but as we have already given that wavelength, the wavelength of a 1 kilo electron volt is given by this value. So what we can do here, we know that E is equal to H nu, then we can write E is equal to nu is C by lambda. So from this, E into lambda is equal to Hc, and Hc is basically a constant. So we can write that E1 into lambda 1 is equal to E2 into lambda 2. So energy of the first one is 1 into 10 raised to power 3 into lambda, that is 1.24 10 raised to power minus 9. And the second energy is 1 into 10 raised to power 6 into lambda 2. So from this, what happens that our conversion or calculation becomes easy. So lambda 2 is 1.24 into 10 raised to power minus 12. That is lambda. And from this, we can calculate frequency. That frequency will be, uh, or frequency is C by lambda. So that will be 3 into 10 raised to power 8 divided by 1.24 into 10 raised to power minus 12. So this will give us a 10 raised to power 20 power to us, and 1.24 by 3 by 1.24, that will be approximately 2.1 something, and that is nearest match to our option B. So option B will be the right answer here. So moving to the next one. An electron and an alpha particles are accelerated by some potential difference lambda e, and lambda alpha denotes the de Broglie wavelength of the electron and the alpha particle respectively. Then we have to find out their relation. Now it is mentioned that they are accelerated by some potential difference. So what they acquire in that potential, they will acquire some kinetic energy. So their kinetic energy half mv square should be equal to the work done on them, and work done in terms of potential is charge times the potential difference, or qv. Here small v is velocity and capital V is potential. So from this, what we can write, and we have to compare their de Broglie wavelength, and de Broglie wavelength is h by p, that is the de Broglie wavelength for an electron. So we have to basically calculate momentum, and energy and momentum, kinetic energy and momentum have a relation that half mv square is equal to p square by 2m. So using this relation, we can write that p square by 2m is equal to qv, and from this, momentum is under root 2m qv. So if we calculate, divide lambda electron by lambda alpha, then h is same in for the both. Under root will be same, 2 is same, and potential is same. So that will become just, as we have p in the denominator, so this will be m alpha q alpha divided by m electron q electron. Okay, so now coming to the charges. So here we have that now charge of alpha particle is twice of the charge of electron. So this will reduce to 2 m alpha by me. Now we know that mass of alpha particle is 4 times the mass of a, basically let's say, a proton or a neutron, because it has 2 proton and 2 neutron inside the nucleus, and that it is basically helium nucleus. and mass of electron is negligible, or if let's say not negligible, then it is basically mass of electron is mass of proton by 1800. It is very small as compared to mass of proton. So if I substitute these values here, so I will get, so from this mass of alpha 2 as it is in the root, mass of alpha will be 4 times mass of proton, and here I will get mp by 1800. Now mp gets cancelled, so what I will get, I will get 3600 into 4, and if I take under root, this will be 60 into 2 and basically 120. So lambda electron by lambda alpha is equal to 120, or lambda of electron is 120 times lambda alpha. This is my approximation, means actual answer will be slightly higher because it is, I think, 1868 times. So as I can see that there is none of the options that can directly match this one, but here option A, that lambda of electron is greater than lambda of alpha, this can be right option as per the given condition. So option A will be the right answer here. Moving to the next one, the graph which shows the variation of 1 by lambda square and its kinetic energy E, where E is the de Broglie wavelength of a free particle. Now for a free particle, we already know that de Broglie wavelength lambda is h by moment. Now we have to convert this momentum in terms of kinetic energy E, and we know that kinetic energy E is p square by 2m. So from this, momentum is equal to 2me under root. So we can write that lambda is equal to h by under root 2me, and if we square, then I will get lambda square is equal to h square by 2m into 1 by e. Now this is a constant term, so basically I can write that lambda square is proportional to 1 by e, or energy is proportional to 1 by lambda square, and that is the option C in graphs. So option C will be the right answer. In the next one, the graph which shows variation of de Broglie wavelength lambda of a particle and associated momentum. So lambda is h by p. So basically lambda is proportional to 1 by p, means we will get a graph like this, a decreasing graph. So that is option D for us. Moving to the question number 51. An electromagnetic wave of wavelength lambda is incident on a photosensitive material of negligible work function. If m is the mass of the photoelectron emitted from the surface that has a de Broglie wavelength lambda d, then we have to find out a relation between the wavelength of the photon and wavelength of the emitted electron. So we know that wavelength of the, or de Broglie wavelength of the electron lambda d will be equal to h by the momentum of that electron, momentum of that emitted electron, and that momentum can be written as under root 2m, where m is the mass of electron, and ee, where ee is the energy of that electron. Now this energy is the energy left on the or I can say energy acquired by the electron. How? Let me explain it in slight detail. That suppose this is our metal surface. This is our metal surface, and here this is an electron. Now what happens? And suppose its work function is phi. Now what happens? That there is a light of some energy E which strikes on the metal surface. So the kinetic energy acquired by the electron, that will be the energy of the, or maximum kinetic energy of the electron, will be equal to the energy of the photon minus the work function. That is the relation from the photoelectric effect we have. But here it is mentioned that photosensitive material has a negligible work function, so we can ignore phi here. So basically energy of electron will be equal to energy of the photon, and energy of the photon will be equal to hc by lambda. So I can substitute E as hc by lambda. So lambda of d is equal to h by under root 2m hc by lambda. Now square both of these, they will get lambda d square is equal to h square into lambda. This will go on top after squaring, and here we have 2mhc. So h gets cancelled, and in terms of lambda I can write that lambda is 2mc by h into lambda d square. So if I match, then I will get 2mc by h into lambda d square is equal to lambda. So option C is the right answer here. Let's move to the next one. Here, the de Broglie wavelength of electron moving with kinetic energy 144 electron volt nearly. So we have to find out de Broglie wavelength, and for that what we can use? We can use relation that lambda is equal to hc by E, and that can be written as 1240 electron volt nanometer divided by energy that is given here 144 electron volt. So basically electron volts gets cancelled, and here what we will get 620, and from this we will get 72, further we will get 310, and from this 336, further we will get 155, and this will be 18. So this is basically 155 divided by 18 into 10 raised to power minus 9. Oh, sorry, we made a mistake. We had to find out de Broglie wavelength for electron, and I just calculated for a photon. So that's actually wrong here. So let me clear this one. So for electron, the de Broglie wavelength is h by p, where p is the momentum. Now here we have been given energy, and energy and momentum have relation that p is equal to 2me under root. So now I substitute the values that h is 6.626 10 to the power minus 34 divided by under root of twice mass of electron, that is 9.11 10 to the power minus 31, into energy that will be 144 electron volts, so into 1.6 10 to the power minus 90. This will be the right solution here. So this can be written like this: 6.626 10 to the power minus 34, and here this is 31, this is 19, so this they will add up to minus 40, and under root is there, so total power will be final power will be minus 20, so it will go on the upper side and become plus 20. And here on under root what we will have? We will have 2 into 9.11 into 144 into 1.6. Now further this can be written as 6.626 10 raised to power minus 40. Now under root of 144 is basically, we know that is 12. Multiply, here we have 2, 9 and 1.6. So what we can write like, we can write them like this: 2 into 9 into 2, just for our approximation. So their under root will give us 3 into 2 6. Now what we can do, this gets cancelled, 1.1 approximately, yeah, 1.1 I think, yes. So further this can be written as I can write 1.1 as 1.2, and keep in mind that I am just approximating here so that we don't have to do heavier calculations. So I just write it like 1.2 divided by 12 into 10 to the power minus 14, and what will this give us? This will give us 0.1 into 10 to the power minus 14, and I can write it like this, that 0.1 into 10 raised to power minus 5 into 10 raised to power minus 9. So this will be nanometer. Oh, I made another mistake, that 31 and 19 will add up to 50. So half of 50 will be 25. So I will get 25 here, and power will be 9, negative 9. So minus 9. Mm, that will be minus 9. And this can be written can be written like this, that 1 into 10 raised to power minus 3 into 10 raised to power, oh sorry, 1 into 10 raised to power minus 1 into 10 raised to power minus 9. Now, as we can see, our answer is in terms of 100. So I can write it like this, that 100 into 10 raised to power minus 3 into 10 raised to power minus 9. So basically, it will be 100 into 10 raised to power minus 3 nanometer. And that is our matching with our option A, given option A. Now, moving ahead, a proton and alpha particle are accelerated from the rest to the same energy. The de Broglie wavelength of proton and alpha are in the ratio. Now we know that de Broglie wavelength for a particle is h by p, and as they have the same energy, so we can write momentum in terms of energy, and that will be 2m times e. Okay, h is constant, e is constant, 2 is constant, so basically lambda is proportional to 1 by under root of m, and from this uh, lambda p, lambda proton by lambda of alpha will be equal to under root mass of proton by mass of alpha particle. Now alpha particle has a mass 4 times as a mass of proton approximately, so lambda p by lambda alpha will be equal to root 4, and that is basically 2. So their ratio will be 2 ratio 1, and that is option A for us. Moving ahead, the electron of mass m with velocity v node I, where v node is greater than 0, enters an electric field E is equal to minus E node I. E node is constant greater than 0 at t is equal to 0. If lambda node is the de Broglie wavelength initially, then de Broglie wavelength at time t is. So we have to calculate de Broglie wavelength at some time t. So let me adjust this question slightly on screen. So it is mentioned that initial velocity is v node I and electric field is minus E node I. And we have to find answer in terms of lambda node. So lambda node will be, it will be h by p node, and that is basically h by initial momentum will be mass times initial velocity, that is v node. Now, as there is electric field, so there will be force acting on the electron. So force will be Q times E, and that will be minus of E into electric field, that is minus of E node I. So basically force is going to increase the velocity because net force is positive. So from that we can calculate acceleration, that will be E node by m, that is force by mass. So velocity after some time t, that will be using Newton's law of equation, that v is equal to u plus at, and that will be u is v naught plus acceleration is E naught t by m. So lambda at certain time t will be equal to h by the momentum at that time, that will be mass times the velocity. So m into v naught plus E naught t by m. Now this can be written as further mv node into 1 plus E node t by mv node. Now this h by mv node term is equal to original or initial wavelength, so lambda t is equal to lambda node by 1 plus E node t by mv node, and that is, I think, given here. Yeah, that is option C. Now if option C is not given, then this can be further written as lambda node into 1 plus E node t by mv node raised to power minus 1, and if we use binomial approximation, then this can be written as 1 minus E node t by mv node. So if this option is not given, then there has to be negative sign here, only then we can mark option B as right. Now moving ahead to the next one, the de Broglie wavelength of a neutron in thermal equilibrium with heavy water at temperature T Kelvin and mass m. Now we know that at thermal equilibrium, that assuming there is only vibrational modes existing, the energy will be, each vibrational mode has a half kT energy. So total for 3 vibration mode, this will be 3 by 2 kT energy associated. Now from this we can calculate momentum. That momentum is 2 times me under root. So this will give us 3 mkt energy, and from that we can calculate wavelength. That will be h by p. So h by under root 3 mkt. That is option B for us. In the next one, electron of mass with de Broglie wavelength lambda falls on target of X-ray tube. The cutoff wavelength lambda node of the emitted X-ray. Now, this type of question we have already solved. Let me show you where we did it. I think. Let me pause the video and find the question. So this is the question. This is question number 51, and we have already solved this one. And here lambda was the wavelength of the photon and lambda d was the wavelength of the electron. Now if I copy this relation, let me copy it, and let's go back to the original question. And what I can do, I can paste it here, and now here it is mentioned that electron of mass m with de Broglie wavelength lambda falls on the target of the X-ray tube. The cutoff wavelength lambda node of the emitted X-ray. So this question is in reverse. We have to, here condition is slightly reversed. So if condition is slightly reversed, here initially we had photon striking to produce the electron. Now we have electron striking to produce the photon. So thus lambdas will just exchange their value. So here we will get lambda electron will be equal to 2 mc by h into lambda photon, that is basically lambda air of square. So this will be the relation. And how we solved it, you can visit our question number 51. There we have solved it already. So option A will be the right answer here. An electron of mass m and proton have same energy E. The ratio de Broglie wavelength associated with them is. So it is mentioned that they have same energy, and sorry, it is a photon, not an electron, and both have same energy. Now for the photon, we know lambda for a photon, that is lambda b, lambda photon will be equal to hc by its energy. And for electron, lambda for a electron is h by pe, where pe is the momentum of electron, and that can be written as like this, 2m into e under root, where e is the energy. Now it is mentioned that e is same in both. So if e is same, what we can do here, we can simply divide them. So lambda of electron divided by lambda of photon will give us h by under root 2me into hc by e. H gets cancelled, and this will can be written as e by 2m raised to power half into 1 by c. So that is the required answer, I think. Yeah. So option D is the required answer here. Now move ahead. Light of wavelength 500 nanometer is incident on a metal with work function 2.28 electron volt. De Broglie wavelength of the emitted electron is. So here light energy is 500 nanometers. So first we have to convert it into this wavelength into energy, and that will be E is equal to hc by lambda for a photon, that will be 1240 electron volt nanometer divided by 500 nanometer. So nanometer get cancelled and we will get 2.48 electron volt. So energy, kinetic energy of the emitted, we can say electron will be, maximum kinetic energy of the emitted electron will be incident energy of the photon minus the work function, that is 2.28 electron volt. So that is basically 0.20 electron volt. So this is the energy, kinetic energy. Now lambda for emitted electron, that will be de Broglie wavelength, that will be lambda by p, and that sorry, h by p, and that will be h by under root 2me. Now value of h will be 6.626 10 raised to power minus 34 into under root, here we will have twice mass, that is 9.11 10 raised to power minus 31. Energy, it is in electron volt, so 0.2 into 1.6 into 10 raised to power minus 19. Now again 31 and 19 will be 15, and they will give us after under root minus 25, that will go on the upper side. So this will be 6.626 into 10 raised to power minus 34 plus 25 divided by, here what we will get, we will get 2.2, 1.6 and 9.11. So let me, this will be 2 as it is, this will be 9.1, let us keep them as it is right now, and this will be 0.32 if you multiply these two. So this will be 6.626 10 raised to power minus 9. Now if we multiply these two, what we will get? We will get zero point 0.6, and zero point 0.6 into 9, what we will get? I think zero point 0.6 into 9, we will get 4.5. So I'm just approximating it, that whole, as we have 0.11 here and 0.232 also here. So I'm just approximating it as root 5, and root 5 is something around 2.2 into, here I have 10 raised to power minus 9. So if I cancel this, what I will get? I will get 3 something into 10 raised to power minus 9. So the only viable option, one option we have less than 2.8, and one option we have greater or equal than 2.8 into 10 raised to power 9. So we will go with option C, as we are getting more than 2.8. If you want exact calculation, you can also do exact calculation. Moving ahead, if the kinetic energy of particle is increased to 16 times the previous value, percentage change in the de Broglie wavelength. So we know that de Broglie wavelength is h by p, and p is 2m under 2me under root. So lambda dash will be, as energy becomes 16, so it will become h by 2m into 16 of E, and this can be written as h by 4 into 2me. So this is original wavelength, so that becomes lambda by 4. Now, so wavelength, initially wavelength was lambda, final wavelength is lambda by 4. So how much percentage change is there? Basically, it is 75%. Or we can calculate it using the delta lambda by lambda into 100. Delta lambda is change in wavelength, that is basically 3 lambda by 4 by lambda into 100 will give us 75%. Next one, the de Broglie wavelength of neutron in thermal equilibrium at temperature T is. So we know that de Broglie wavelength is h by p. In terms of energy, it becomes h by 2me, and it is at thermal equilibrium, so it will have, assuming 3 degree of freedom, so it can E will be equal to, each degree of freedom has half kT, so for 3 degree of freedom 3 by 2 kT, so it will become h by 3 mkt. So here this can be written as h by under root 3 mk, as these values are known to us, and into under root t. Now value of H is 6.626 10 raised to the power minus 34 divided by under root 3, mass of electron 9.11 10 raised to the power minus 31 into K, where K is Boltzmann constant, so that is 1.38 10 raised to the power minus 23 and into 1 by under root T. Now after solving this, what we will get? We will get approximately 30.8 by root 2 into 10 raised to the power minus 10. Now keep in mind, I have already solved this, that's why I am writing it, because this is a time consuming calculation and I have given the expression, you can calculate yourself. So 30.8 under root divided by under root 2 angstrom, that is option D. Next one, if the momentum of electron change by p, then de Broglie wavelength associated by changes by 0.5%. Initial momentum of the electron will be. So as we can see here that change in momentum is small. So we can also use error analysis. And so uh, lambda is basically de Broglie wavelength h by p. And from this momentum is change, we have to find out delta lambda. So delta lambda by lambda from the error analysis, that can be written as delta p by p. So from this, change in momentum is p. So we can write that delta lambda by lambda initial. Delta lambda is change in wavelength. Lambda initial is the initial wavelength, is equal to delta p, where delta p is the change in momentum. So it will be p by P initial. Now this change in lambda is given in percentage, so what we do, we multiply 100 on the both side. So this change is equal to 0.5%. So this will be 0.5 is equal to P by P initial into 100, and from this can be done as half, so half is equal to P by Pi into 100, and from this we can write that P initial will be 2P into 100, or basically 200 of P. That is option A for us. Next one, an alpha particle move in circular path of radius 0.83 centimeter, presence of magnetic field. This value the de Broglie wavelength associated with the particle will be. So here alpha particle is moving in the circular path. So for a circular path, we know that radius in a circular path is equal to mv by qb. From this velocity, or basically we need de Broglie wavelength, so means we need momentum, and momentum will be equal to, from this relation, mv is equal to qpr, and de Broglie wavelength will be, lambda will be h by p. So h by qpr. Now h is 6.626 10 raised to the power minus 34 divided by q, that is charge of the alpha particle, that will be twice the charge of electron, so 2 into 1.6 10 raised to the power minus 90, magnetic field 0.25, and radius, that is 0.83. After solving this, what we will get? We will get 0.01 angstrom, and that is basically option D for us. For the next one, electron used in electron microscope are accelerated by a voltage of 25 kilovolt. The voltage increased to 100 kilovolt. The de Broglie wavelength associated changes by. So we know that lambda is basically h by p, and that p is momentum, and it can be written as 2m times E, where E is energy, not electric field, it is energy. Now we have a relation that work done in terms of potential is Q times V, where V is potential applied, and Q is charge. And we have know that energy and work has the same unit, so we can displace them or replace them. So this becomes H by 2m into QV. So basically 2 is constant, mass is constant, and Q is also constant for electron. H is constant, so lambda is proportional to 1 by under root of V. So from this, lambda 1 by lambda 2 will be equal to under root of V1 by V2. So lambda 1 by lambda 2 will be equal to V2 is 100 and V1 is 25. So this will be 4 under root, which will give us 2. Lambda 1 by lambda 2 is 2, and lambda 2 is lambda 1 by 2. So it decreases by 2 times. That is option A for us. Moving to the next one. A particle of mass 1 milligram has the same wavelength as of electron moving with this velocity. The velocity of the particle is. So we know that for particle, de Broglie wavelength will be h by p. Now h is constant, so lambda is proportional to basically 1 by p. So from this we can write that lambda into p is constant. So if lambda into p is constant, uh, basically lambda is also same here. So if lambda is same, so p is constant. So momentum is constant, so we can write m1 v1 is equal to m2 v2. So m1 for the we can say mass, that is 10 to the power minus 3 of the particle into v1 is equal to m2, that is mass of electron 9.1 into 10 to the power minus 31, velocity of electron 3 into 10 to the power 6. So from this v1 comes out to p, this goes into denominator, minus 3 goes up, becomes positive. So that is 27.3 into 10 to the power minus 31 plus 9, and that will be 27.3 into 10 to the power minus of 22, and that will be 2.73 10 to the power minus 21. That is option D for us. Now moving ahead, if the particles are moving with same velocity, then the de Broglie wavelength is maximum. So we know that lambda is equal to h by mv. Now h is constant, velocity is constant, mass is there, that will be different for each, and as we know that lambda is inversely proportional to mass. So for maximum de Broglie wavelength, mass has to be the lowest, and that is possible for beta particles, as beta particles are basically electrons, and electrons have the lowest mass. The wavelength associated with the electron accelerated to a potential of 100 volt is of the order of. So we know that lambda is h by momentum, that is 2me under root, and energy can be written as further as 2m into qv. So substituting values, it will be 6.626 10 raised to power minus 34 under root twice mass 9.11 10 raised to power minus 31, charge 1.6 10 raised to power minus 19, potential 100. And when we solve this, we will get 1.22 angstrom. That is option D. Coming to the last one for this video, the de Broglie wavelength corresponding to particle mass m velocity v has a wavelength associated with it. So de Broglie wavelength is h by mv. That is option A for us. So with this video is complete, and this chapter is also complete. Hopefully you have liked this video, find it useful. If you find it useful, then do share it, subscribe to our channel. Also, if you like to support us financially, scan these QR codes. It helps a lot when you donate something. With this again, thanks for watching, and we will meet in next video.